bit manipulation. Then I'll show you how I did my pairing index when my current implementation of pairing index. Does that make sense? All right. So, yeah, who wants to talk about the pairing index? I'll go. You want to talk about yours? Okay. So you just, I don't know how we'll do this. You can just explain it, then I would write it out as you're explaining.
Can I share you
The screen, you don't share your screen?
can I share you the link
To,
and the GitHub?
okay, sure. But I'm more interested in the idea behind
Yeah,
it.
okay.
You know, like when you now start, you have to pass the code and pass the idea. Do you get what I mean?
So it's
Over. You know how you did it, right? Okay, so let's say 3 variables. Right? And let's assume we wanted to evaluate at B. B is the only thing interesting here. Okay. So how would you go about this with your style?
right. So I assumed my y1 would always start from 0.
You assume your y1 will always start from 0.
Yeah.
Okay.
Like the first value of y1
Yeah.
would always be 0.
So you're talking about your pairing, right?
Yeah, my parent.
So you're always going to be pairing something that. So let's say you're pairing 0,
So
0.
all my y1s would be where that bit
Bit
is
is
set to 0.
okay. Yeah,
basically.
that makes sense.
And then the y2 equivalent is where it's set to 1.
Yeah, that makes sense.
Right. So I initialize like my first y1 value,
Mhm.
y1 paired to 0.
So the first one, right? So
Exactly.
0, 0, 0. Well,
So what I did was
also to this one.
finding the y2 equivalent is kind of straightforward, like using big manipulation. But the issue came like where you needed to find the next y1
So
value.
let's first talk about how you find the y2 given a y1.
Okay, giving a y1.
Yes.
Okay, so basically, I look for what that variable's index is set to the power of.
So A, B, C, right?
Yeah.
So A is the what?
So I did the index of A is 0.
I did it,
The
yes.
index of B is 1.
Yes.
The index of C is 2.
Yeah.
But if you look at it, A is actually like 2 raised to the power of 3.
So what you're
2 raised to the
saying,
power of 2, sorry.
A is this, right?
Exactly.
Okay.
Exactly. So what I did was basically to add the current y1 index with that value.
Okay. So what you're saying now is that, let's say we're looking for B, right?
Yeah.
It's going to take the y1. So once it has a value, it can figure out the pair by ORing that value with the target.
The target power.
So in this case, the target power is B, right? So I'm trying to evaluate at B,
Yeah.
and that's like 0, 1, 0, right? So it's going to OR it with 0, 1, 0, which will give us 0, 1, 0. So ORing is like you're doing element wise, and if any of them is 1, then the result will be 1, right? So this is like 0, 0. Nothing is 1. That's why the result is 0. Then this is 0, 1. There's a 1 there, so the result is 1. And this 0, 0, so the result is 0. This makes sense to everybody, right?
No,
Wait, what doesn't make sense? Is it the ORing?
I don't understand.
Okay, so
Okay, wait, so. Okay, yeah, go on.
okay, so what all basically does in bit manipulation is if you have 0 and 0, right?
Yes.
If you are ordering any value 0 and 0, you have 0. It's kind of like an addition
Yes.
property basically. So if any value that you are ordering is 1, your result is 1.
Yes. So this is the truth table. So
Okay.
0.
Yes.
Yeah, all.
This was 1.
Okay, you are saying orange.
Right? So 0 or 0 is 0.
Yeah.
0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. You get?
Yeah.
So this orange.
Okay.
Oh.
Alright.
How do we spell all?
Please continue. Thank you.
Okay, so that was how I got my Y2.
So how he gets his y, does it make sense how he gets his y2? It doesn't make sense. Okay. So what it does is that you will have a y1. So you know it's pairings, right? So you have something paired with something. So if he has the thing on the left side, he can know the thing on the right side by just doing the OR. So let's therefore do it normally, then we'll now see it with the OR, right? So let's say we wanted to pair this. What would this be paired with? If we're evaluating a B.
0, 1, 0.
Yeah, so 0, 0, 0 is going to be paired with 0, 1, 0, right? Then what of 0, 0, 1?
0, 1,
Makes sense, right? What of 0, so this is
1,
where
0, 0.
you need 1, 0, 0. So 1, 0, 0 will pair with what?
1, 0.
And 1, 1, what's the next one? 1, 0, 1.
1, 0, 1.
This is the pairing for B, just like looking at it normally. Now let's use the OR ring. So once he finds this, he can get to the other side using what he's about to describe now. So I'm just going to do it here again, right? So the value for B is what? 0, 1, 0. Does it make sense that the value is 0, 1, 0? Yes. Makes sense? You can also get that by 2 to the power of what?
2 to the power. So I find how I get the power is
Yes.
the number of variables minus 1 minus the index of that
Yes.
variable.
So that will reverse it. You know, technically, like if you look at this from an array perspective, A is 0, B is 1, and C is 2. But it's doing it the other way, which is like 2, 1, and 0. Right? Because 2 to the power of 2 is equal to 4, which is equal to 1, 0, 0 in binary. But you can also just think about it as like A is on.
Yeah.
So there's a 1 there, and then the rest of them are zeros. Does that make sense? So depending on your target, you get like the power, the equivalent, that's the 0, 1, 0 for B, and then 1, 0, 0 for A. So now since we're doing B, we just look at this 0, 0, 0. Then we OR with what? 0, 1, 0, right? 0, 0, 0, 1. So that's 0, 1, 0, right? So this checks out. Now let's do 0, 0, 1, right? We OR with 0, 1, 0. 1, 0 is 1. 1, 0 is also 1. And 0, 0 is 0. This is 0, 1, 1. Checks out, right? Then 1, 0, 0 is what? 0, 1, 0. 1, 1, 0, right? Checks out. And then finally 1, 0, 1 or 0, 1, 0. That's what? 1, 1, 1. Checks out. Okay? So when you know what is at this side, it's easy to know what is at this side. But then there's a problem, right? It's not always easy to know what is at this side. For A, it is this first 4, right? So it's easy for A. For B, it is what? This first 2, then it skips 2, then it gets the next 2, right? While for C, it is this one, then this one, then this one, and then this one. You get? So you need another algorithm to figure out what is going to be on the left side. Then once you figure that out, you can apply the XOR. So what's the algorithm for figuring out what's on the left side?
So like you said, after outlining all the different values from 0 to 7,
Yeah.
you still recognize the pattern that for A, you kind of have the first 4, then you are skipping the next 4, and if there was any value after that, you are basically using that, right? And for B, you are taking first 2, skipping the other 2. So if you look at it, it's actually like skipping by the power of like that value as well.
Yes. So let me now
Okay. Yeah, you can interpret.
explain what it's saying. So for every target there's a power, right? So A is what? A is
4.
2 to the power of 2, right? Which is equal to 4, which is also equal to this 1, 0, 0, right? Then B is going to be 2 to the power of 1, which is 2, which is equivalent to 0, 1, 0. Give me a sec. Then C is what? 2 to the power of 0, which is equal to 1, which is equal to 0, 0, 1, right? So this power plays a critical role in both the going from y1 to y2 and also figuring out what yes, what the next y1 is. So his algorithm basically is that you pick the power number of elements. So yeah, like I started from the top, right? So for A now, you're going to pick 4 elements sequentially. Then once you are done picking, you're going to skip 4 elements. Then you pick another 4, then you skip on and on like that. But in this case, we'll get to the end of the list before we need to pick anything again. So let's do for A. So A is going to be 0, 0, 0, 0, 0, no. Yeah, actually, 0, 0, 1, 0, 1, 0, and 0. My head is slow today. 0, 1, 1. So this is A. Then you skip 4. So you skip this, you skip this, you skip this, and you skip this. By that time you're already done, right? You have reached the end of the list. So you have gotten all the y1 for A. Then you still use that 4 to do your OR, right? To go to the next side. So this is going to be 0, 0, 0 or 1, 0, 0. Exactly. So you do OR 1, 0, 0. You do OR 1, 0, 0. Do OR 1, 0, 0. Do OR 1, 0, 0. Right? So this is going to be 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You get? And that's how you do like the pairing for A. So now let's do for B. For B, the power is what? 2. So you are going to take the first 2, which is what? 0, 0, 0, then 0, 0, 1. Then you skip 2. You skip this, you skip this, and then you pick the next 2. Then you skip this, and you're done, right? Then you XOR with what? 0, 1, 0, right? So you get what? 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, which is exactly what we have here. Does it make sense? Is it clear? Okay. So that's how Uche does it. Who did it a different way? Okay, we have so many people that do it different ways. Okay, how did you do yours?
It's exactly like the way you did it now. I don't like pattern of like finding unique things.
Okay,
That's I didn't go as far as like using discovering like the power
okay,
pattern.
okay,
I just like created a separate function,
okay,
right? Goes through the whole array of points.
okay.
Right?
Wait, of points. That's the evaluation.
Yeah, the evaluation.
Okay,
Kicked out because now if I'm using if I'm just the way I was doing it before that I was just using the first form. Right?
Okay.
The first form will work for only A. Which is not
Yes.
like the next variable.
Yes.
And instead of just looking through half of the array, I
Okay.
looked through the whole array.
Okay.
And found out unique pairs. Right?
How do you find unique pairs?
Like now, if I'm using B,
Yes.
if I'm using B, if I look through the whole array,
Yeah.
I'll find that okay, the first one and
Okay.
the second one give unique pairs. But now the next one and the third and the fourth one will give the same pairs, but now put the other way around.
So what do you mean by unique pairs, or how do you detect that there's a unique pair?
Now looking at this now, a pair is like 0, 0, 0, 0, 1, 0.
Is there a better way? Should I write out an array of the?
No, like this now, the way
It's
you've
good.
written it at that top right, that pattern in maths.
Yes.
Guys, yeah. At that top right, a unique pair is 0, 0, 0, 0, 1, 0, 0, 0, and 0, 1, 1 for B.
Mhm.
Right? So
Mhm.
we're picking like B.
Mhm.
Now, if you look through the whole 8 elements, you're going to find these pairs. Right?
Mhm.
We are going to find if you like if you look through everything, you pick each one of these ones 0, 1, 2, 3 to 0. Right? You're going to find a unique pair.
How will you find a unique pair?
Like this guy now, right? It could be the other way around.
Which guy?
Like the first one, 0, 0, 0, 0, 1.
Are you assuming that you already have this?
No, I'm not assuming that you already have.
Okay.
I'm saying that now, if you look through the array, like if you look through the array, and for
That's
every,
this array.
Yes, and for every single guy, you're finding a pair,
Yeah.
right? You're going to find a pair that is the same but the other way around. Like 0, 0, 0 goes to 0, 1, 0, but it's going to be 0, 1, 0 goes to 0, 0, 0.
Can you define this as an algorithm? Like, imagine I don't know anything, right? And then just tell me step by step what I need to do.
Okay,
Okay,
now
so what am I starting with? What's the input to your algorithm?
my input to my algorithm is going to be like the evaluation for
Evaluation for the polynomial. Okay, so I have a polynomial that has 8 elements, right? Let's just assume 1 to 8. Oh no, let's do 0 to 8, just so it might be easier. 7. Okay, so what do I do next?
Now I'm looking through each element,
Okay,
right?
yeah.
And I'm looking through each element, right?
So the first element is 0.
First element is 0. I have 0, 0, 0.
Okay,
The index is 0, 0, 0.
Okay.
Second element is 0, 0, 1.
yes,
Right? Now, if I pick 1, right?
yeah.
To find a pair,
So
right?
you're picking 0, 0, 0 now, right?
The pair
Okay,
for 0, 0, 0 for B
yeah.
would be 0, 1, 0.
How do you compute that pair?
I'm using like this one, I'm using a left shift and XOR.
Okay,
Using
so
XOR and
tell
left
me
shift.
exactly what I need to do to 0, 0, 0 to
So-
get a pair.
Now, when you left shift,
Okay,
on left so I did like okay,
and left shift how many times?
right? I'm just left shifting once.
I should left shift once.
Once.
Why once?
Because I'm going to like when I get the value of like the left shifting once, right? I'm going to do XOR.
Why am I left shifting once? Why is Amela left shifting twice or 0 times? It does it depend on B somehow?
It doesn't depend on A, B, or C. It's just because like I'm trying to like
Okay. Okay, so I shift once, right?
yes.
So left shift once.
Yes.
That would be 0, 0. Right? Okay, one no, that would be 0, 0, 0. Are you talking about right shift?
So left shift.
No, left shift is like if you have 1 and you left shift, that's going to be 1, 0.
Okay.
And if you left shift again, that's going to be 1, 0, 0. But if you right shift, you're going to go back up. And if you right shift again, you're going to go here. So are you doing left shift or right shift?
Left shift.
You're still doing left shift. Okay. So if I left shift 0, 0, 0, I'm going to get 0, 0, 0. We lost check now. No, I can't. No. It might be wrong. I might be wrong though. So let's say we start with 1.
0, 0, 0. Yeah, let's say 0, 0, 0.
No, 0, 0, 0, always 0, 0, 0. So that doesn't show us anything. Let's try 1. But I can't represent it in binary now. So let's say A is 1, right?
It's 1, yeah.
Then we now left shift 1, right?
Yes. F equals to A. Yes.
Right? So we can print out the result. Let me print it in binary actually. I don't know. I think I'm not sure. Right? Alright. I don't know. I don't know this correct, but I think it is. Yeah. So you see A is 1.
So now
When I left shift, there's 0. You good?
yeah, I guess.
Okay.
So what I'm doing is that I'm saying 1 left shift my current position.
Okay.
So can you
Oh, I see what you're saying. I think it's trying to get your power, but in a different way.
yes.
Okay. So it's not you're not shifting the. Okay.
I'm saying 1
Uh-huh.
left shift
Uh-huh.
my current position, which is B, which is going to be 0, 1, 0.
Your current position, that's your target. The
Yes.
target evaluation,
Target evaluation.
which is B.
Yes.
That's 1.
Yes.
So it was A, what would that be? Would that be 0 or 2? To be 2. So you're also doing, so it's just the power thing. It's just the power thing.
Just the
Okay.
power thing.
Okay, so what do you now use that for?
Now I use
You
that.
off.
Yes, I don't use or I use XOR.
Use XOR
Yes.
or more. Okay, so you're always going to have 0, 1, 0 for B in this case, right?
Yes.
Okay, so you're XORing.
Yes. So now, when I like the value of the 1, then so I'm XORing, like I'm XORing
Yes. You're iterating over every array, right?
Yeah.
And then you're XORing each element with what? With what we just computed, right? So now, are you going to do 000 x or 010?
So let me check my already.
I think that's what you're doing, Sha. I think. So are you going to have duplicates?
Yes, I'm going to.
You're going to have duplicates.
Yes, I'm going to have.
Yeah, so you're XORing. That makes sense.
Yes, so instead of me having duplicates, right, I'm going to like check
If
if I found one.
yes.
If I found one, I'm just going to skip to the next to find. I'm going to just to find unique pairs,
Yes.
and that I'm only having 0 zeros at first and
Yes.
0 ones at the end.
Yeah. So how do you know so let's say you found one. No. If you do for 000
Yeah.
x or 010, you will get 010, right?
Yes, I'm going to get 0 ones.
You have not seen that before.
Yes.
What do you do with it? Do you store it somewhere?
I know it's somewhere.
What do you now do?
Okay, yes, I'm pushing it to a vector.
You're putting it to a vector.
Yes.
Are you pushing tuples?
Yes, it's a tuple.
You're pushing a tuple.
Yes, I'm pushing it.
The
No,
zero.
I'm not pushing it tuple.
Okay.
I'm just pushing the coefficients.
Okay.
Right. You know that normally all we are doing
Oh,
is
he's pushing the y1 and y2, not the
exactly,
index
you're not
itself.
pushing the index
Yeah, but
themselves.
okay.
So what I'm trying to do is that giving this guy, right? Giving so what I'm trying to do is that giving this guy, I'm getting I'm getting a tuple, a vector of tuples.
So you're pushing tuples.
Yes, I'm pushing tuples.
But you say you're not pushing tuples.
Sorry,
Okay.
so I'm pushing a vector. I'm pushing tuples to the vector, right? To the array. Now the tuples I'm pushing are the y1 and y2.
I don't get. Okay. I get, but I don't see how we'll reach them.
Yeah.
So let's now do it. I have a better idea of what you're saying. Okay, so 000, right?
Yeah.
X or 010, right? I'm going to get 010.
Yes.
So what do I do with this 010? Or what do I do with anything?
I'll move to the next guy.
But you just forget about it.
No, I'm not forgetting about it.
So what do you
So,
do?
like, I'm going to check.
Your instructions are not precise. Yeah. Okay.
Look at the code, look at the code.
I have to look at
Yeah,
it.
look at it. Please, can we do that for C?
The first one. Okay, just look at your code and get it precise. Then we'll come back.
Yeah, the C part.
Yeah. So for C, right, it's going to be 2 to the power of what?
It's 0.
0. So that's power of like 1, right?
Yeah.
So this means that we'll pick the first one, then we'll skip one,
Okay, we'll skip one.
then we'll pick one, then we'll skip one, then we'll pick one, then we'll skip one. So let me do that now. So it's like 000, then you skip 001, then you go to 010, then you skip 011, then you go to 100, and you skip 101, then you go to 110, and you skip down, and you're at the end of the list already. Then when you're done, you now XOR with ones. That's just adding 1 to the back. Not XOR yet. Or. So 001, 011, 101, 111. Does it make sense? So this is how we first of all did it. Like when we first implemented this was also the method that we used. This was also the method that we used. Yeah. But we found a faster one. Have you got your precision now? Okay, let's start. So we're looping, right? 000, okay? XOR 010. Get 010. What next?
So now, I'm going to check if the first guy, which is 000,
Okay.
if it is less than the pair I found,
Less than which pair?
less than the 010.
So if it is, then you index the array at.
If it is, then I know that that's the unique pair.
Yes.
Right?
Yes.
So I just like get the coefficients of
Both of them.
indexes here,
And push it to a
then
tuple. I get you now. Okay. That makes sense. It might be faster than the other one actually. Let me see. It It might be faster actually. But I don't know. You have to benchmark. You guys will have to benchmark. So you benchmark your code. I think that's what you guys should do over the weekend if you have finished your implementation. Try and use like criterion to benchmark your code. I'll send the parameters that you should use. So we'll now doesn't really matter. It doesn't really work like that actually. The reason why it's what we call different specs. Yeah, so that's my benchmark codes, then push. Then I'll run it on one system. Okay. So this is what it's doing. This is what it's doing. This is what it's doing. It actually might be faster than my I don't know yet. Let's see. So what it's doing now is it's going to iterate over the list, right? The index. So everything that we're doing on this like binary rep, we can also do on regular decimals, right? It's exactly the same thing. The computer just allows you to view it in different ways. So what it's doing now is it's going to compute the power, that same power, right? So that's going to be, in this case, it's going to be 0, 1, 0. So this is what it's going to use for everything, right? So it's going to iterate over the list.
Wait, what 0, 1, 0?
You know why we're evaluating at B,
Okay.
right? So B is going to be 0, 1, 0, which is 2 to the power of 1. Does it make sense? So it has a vector that's going to have all the pairs in it. So what it does is that it starts at 0, 0, 0. Then it does the XOR. So XOR is like this. It gives you a 1 when they are different. But if they are the same, it gives you a 0. Do you get? So 0, 0, 0, 1, 1, 0, 1, 1, right?
Yes.
Then XOR. Is this XOR? I think it's XOR, right?
Yes,
Yeah,
that's
this
all.
is Excel. This is Excel.
This is excellent.
So what is OR?
What is this?
Okay.
Right.
So if they are the same, you're going to get 0. Regardless of whether it's 0, 0 or 1, 1. But if they are the same, you get 0. If they are different, then you get 1. So this is 0, this is 1, this is 1, and this is 0. This is XOR. It's different from OR. OR is OR is
What is it? One is one.
One is true. One is true.
so this is OR. This is the difference. So the question now is like, what does this difference achieve? Yeah. So let's say I had 0, 0, 0 or 0, 1, 0. I'm going to get what? 0, 1, 0, right? Now let's say I had 0, 1, 0 or I'm still going to get 0, 1, 0, right? So wait, let me see. What if we did XOR? I'm trying to see what this might.
0, 0, 0, 1, 0.
Then
1, 0.
you know they're all the same. So what his does is that you always get the other pair, right?
Yeah.
Regardless of 0, 0, 0 is to 0, 1, 0. So if you start with 0, 0, 0, you get the other one, and if you start with 0, 1, 0, you get the other one. Why the OR only goes one way,
Yes.
only from zeros, so 0, 0, 0 to 0, 1, 0. Do you get? You don't need to worry too much. I was just trying to see what the difference might mean. Okay, so what it now does is 0, 0, 0, right? You XOR with 0, 1, 0. And then you get 0, 1, 0. What is 0, 1, 0? That's 2, right? So it's checking first if the two values he has, if this is the first time he's seeing it, technically. That's technically what it's doing. So it's going to do, is this less than this? Is this 0, 0, 0 less than the 0, 1, 0? So this means that this is like the first time he's seeing this, technically. So what it's going to do is that it's now going to take so this 0, 0 is basically like 0, and this is basically 2. So it's going to push the evaluation at index 0 and the evaluation at index 2 to a tuple. Yes, as a y1 and y2. So that'll be 0 and 2. Does that make sense? Then it's going to do it for the next one, right? Which is 0, 0, 1 or 0, 1, 0. Which is going to give 0, 1, 1. 0, 0, 1 is still less than that. So this is the first time it's saying this, right? This is 3 and this is 1. So it's going to push 1 and 3 in. Now, it's going to go to the next one, which is what? 0, 1, 0, right? And then it's going to OR it with 0, 1, 0 also, right? So that's going to be... Now, this is less than this. So this must mean that he has seen it before, right? Because we're always going from smallest to lowest. So you must see this... Yeah, smallest to the biggest. So you must see the smallest one first. So if you are seeing the bigger one first, then that means that you have seen it previously. So it skips this. This means that 2 has already been paired with something, so it doesn't need to touch it anymore. And I think if you go to 3, you'll also have the same scenario. So the next thing that will happen is you go towards 4, right? Which is 1, 0, 0, right? Then 0, 1, 0, 1, 1, 0. This is what? This is 6. And this is 4. Right? 4 is less than 6. So it pushes it, 4, 6. And then it just continues this process until it has like 5, 7, right? And then that's how it does it. Then it now does the linear interpolate and evaluate for those values. And this is like his linear array. So you can map this to something that will do the linear interpolate and evaluate. Does this method make sense? Yeah?
But we are talking about this speed the other time. But compared to the other one,
Yeah.
This one is still going to go to big O of n.
Yeah.
The other one will go technically like n over 2.
How?
Because you are not going over the whole array. You are going over half of the array and getting the other value yourself.
Not necessarily, right? I'm
Because
coming.
Even if you step 2, 2, you are still going to go over half of the array and then you are getting the other value yourself. But this one you are still going to go over each and every one of the arrays. So that's like big O of n versus n over 2.
Wait, I'm coming. So you are going, then sometimes you won't continue, right? You'll skip.
Yeah, but you checked it.
Wait, I'm coming. So you go, then you skip, then you go, then you skip, then you go, then you skip. So let's say we're evaluating C, right?
Yes.
It's almost like as if you're still iterating over the entire array, right? Because at some point you have to get to the second to the last one, technically, right?
Yes.
Does that make sense?
Yes, you get to the second in that, but you kind of like, E is giving a kind of check that, okay, check if this plus this next value plus this next value is going to give you a kind of, after dividing it, what's that percentage?
Which percentage?
After doing the mod with that
Is it XOR?
power. No, not this XOR. After doing the modulo with the power, if it gives 0, then skip that point and go to this point.
The second one?
No, the first one.
The first one? Okay, you're talking about the stepping, right?
Yes. You do a check so as to skip that particular
Yeah.
value.
Yeah, performance is not as, how do I put it?
Straightforward.
Yes, it's not as straightforward as, like that modulo operation now might be a crazy operation. Modulo operation is like dividing, then getting the remainder.
Yeah.
That might be more than one CPU cycle. But XOR is just one CPU cycle. Like a dedicated CPU infrastructure just for XOR. You get? So that's why I said you have to bench. All these ones that we're doing, we're just guessing. You have to actually bench to know whether it's faster or slower. Does it make sense?
Yeah.
So we don't know. We don't know which one. Does anybody have another method?
Yeah.
I think
Check.
this is like kind of close to where
The second one?
yeah,
The second one?
the one that Michael looked at.
Okay.
Mine still uses the XOR.
Okay.
But then what I noticed was if you for instance this X that pair the 0, 0
The first one?
yeah, so this pair here,
This one?
yeah, like let's just observe everything now. Let's say we want to evaluate at any let's say A or let's say A. So
Okay, A.
you have the A bit on and you have the B and the C bit on, so that's like 1, 0, 0.
That's like the power for A. I said that's like the power for A, right?
Yeah, yeah.
In the other.
So I don't know this parent. What's
This
parent
was that one is for
This one is for C.
C.
What's okay? So C is 001. C is 001.
Yes.
So if you XOR these bits like directly,
Which bit?
like the 3 bits, like XOR the 3 of them together, we XOR 0 it, we are going to get C, like the index.
Oh.
001.
Right.
So if you XOR this, you get 001. Okay. So figuring out this pattern now means that for any B or A,
Okay.
for any B or A, if you are looking for B, the B pair will also when you XOR them together,
Yeah.
they integrate B. So that means you can
So how
just,
do you take advantage of this?
yeah, so you can just take the index. So let's say the target, I call it the target.
Yeah.
So the target is, let's say C, which is like
001. Yeah.
I'll take the target and because I don't want to like loop.
Please don't tell me. Okay.
So when I take the target, I'm going to XOR it with 1 to see if I get so 1. So
Wait.
I have like,
Let's say your target is what 001, 010, right?
yes.
So what are you going to XOR this with?
So I'll start from like the first.
000.
Yes. So if I XOR it, I'm using like a hash set, not to prevent duplicates.
Okay.
So when I XOR it,
Yes, you get the equivalent.
yeah, I'll get the complement. So and I have a condition now. That means if that complement is in the hash set, if the complement is not in the hash set, right,
Then
I'll
you
just
push.
add it.
Yeah.
I'll just push it. But if it is in, I'm
Then
going
you
to
pull.
push the complement and then the number in the yes. Not the number in the evaluation form, the bits form. So let's say I do my target is 001. I XOR it with 001.
Yeah, that was it. So let's say this is your hash set. Right?
Yeah.
So we start with 000.
Yeah.
Then XOR with what?
So the target,
That's B, right?
yeah.
So then you get 010.
Yes.
So you
it's
check-
not in the hash set.
Yeah, it's not.
So I just put it there.
As what? Is it a number?
No, just 0, 010.
Okay. Then we go to what? 01001, right?
Yeah.
Right?
So it's not there, I put it there.
Okay. Right?
Yeah.
This is what? 000.
Yeah. I put it there.
You also put it there?
Yeah.
Wow. Okay. It's not there also, right?
Yeah, I put it there.
Okay.
I can still optimize it. Bro.
Yeah, no, but let's just get the idea first. Then this is now 100, right?
Yeah.
It's not there either.
Yeah.
It's fine. Like, no. I mean, like, am I following it correctly?
Yeah.
Like, this is expected. Okay. 110, right?
Yeah.
So now 110. Okay, I think we might. Right?
I think it's supposed to be 101.
Sorry, I made a mistake. Yeah. Thanks.
Yeah.
Okay. And then what? One. I didn't B. I didn't B.
Okay.
How was I? So 010, right?
Yeah. That's 1, 0.
Right?
Yeah.
Not there either.
So what operation is that?
XOR. Yes. So like if they are the same, then it's a 0. But if they are different, then it's a 1. Then 111. Okay.
So that's
101. Not there either. So nothing is there.
I think, no, let's use A first.
Are you sure it's
Let's
empty?
see.
There is not.
Hey.
I think we might have missed something in the explanation. But how can there be no? Okay,
He
yeah,
said
generating
the
every-
answer contains the
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 previous-
complements, the complements.
But the code works.
Yeah.
So
You just want to- Let's do for you first.
Let's do for instance.
right?
Yeah.
What? Right? Are we doing our XOR wrong? We're not
Sorry,
now.
just you.
I think it sends me your code.
Let's do for you.
Let me look at the code. Is this getPerf function, right?
Get pair is XOR.
So you have norms. What is norms?
The array.
Array of what?
That's the array that we're looking for.
Okay. So result is a vex. Sin. So you have two vex, okay? Sin is a hash set. Then you iterate over every norm. Norm? Wait. When you say the array we're looping through, are you talking about the index of the array?
In there.
Where do you call this?
I can go to test. There's a test finding pairs.
Boolean hypercube. What's in the Boolean hypercube?
The in that 0, 0, 0, 0, 0, 1.
But as you tell too.
Yeah.
So that's just 0 to 0, 1, 2, 3, 4, 5, 6, 7, 8.
No, like it's still like the number.
That's like, I mean, like, they're in decimals, right?
I know decimal.
How are you not representing as you tell too?
It's like 1, 0, 0 is still the 32.
1, 0, 0. Oh, wait. You're representing the binary
Yes.
as a number.
Yes, yes,
Okay, so the is 101, like
Yes.
101
yes.
decimal.
Yeah.
Okay. So that means 001 will just be 1.
Yeah.
Okay. So you have that. And in order, right? 0, 0, 0, 0, 0, 1. Okay. So you have your Boolean hypercube, then you're iterating over each one. Then you get the complement. Okay, that's not what we were doing then. That's not what we're doing then. But now, that 101 is no longer 101 in binary. Like if you check this now, right? Let's say we said A was 101. From where? We said A was 101. The binary representation is Playground can be slow sometimes.
What's up?
The playground. Um, So see what 101 looks like now. I don't know if you can see it. This is 101. This is what it looks like in binary. So when you are building your XOR, it has been against this, not 101 itself. So now the question, like, what's the intuition behind this? How did you?
The intuition is that if you can find, like if you draw the two of them,
Yeah,
and you can find that value
yeah,
in the app set,
yeah.
what I'll just do is I'll just push complement and then that number.
So what pairs would allow you find that?
Yeah.
So what pairs, like 101, and what would match in your scenario? Is it
It
the,
now depends on like
the target?
Yes.
So let's say the target was B. So that would be 101 and 111.
No, it will be 010. The target of B is 010.
Yeah, yeah, yeah. But it's pushing the
That'll be 010. Yeah, that'll be 101, 111. That's
111.
what we get, yeah.
So let's see what 111 is. Right? So this is what they are. This is what 101 and 110 looks like as bits. So you're saying that they should match if you XOR one of them with the target, right? Okay. So let's say 010. But this one now is binary, right? So that's like, but when you're ORing, that's your target. What is it? I need to look at your code again, just so that we don't make a mistake.
The target is also like a normal AU32.
So what do you pass? Like, is it just B?
Said? Not the value, like the.
Or you also pass? So you moved all your bit stuff over to the decimal. So you're not actually ORing with the bits. So this your target is something like this, right? 010. Literally 010. So you print line this is what your target actually is. Now let's OR it.
Yeah, so.
Let's OR it and see. So A, right?
Yeah.
Both of them should give the same thing, right? There should be a match.
So if you do A, is your target. B,
It should give B.
Yeah.
Oh. Okay, okay. Let me just write it. So this is A, this is B, this is target. So yes, when you do A, XOR target, you do get B, right? And then when you do B, XOR target, you do get A. So they match, and it works. But it's just that you are doing it in decimal,
Yeah.
as opposed to
I'm not able to figure
in bits. Yeah. And that's the case for him too, right? Like when you XOR, it always gives the other pair, right? So it's exactly the same thing. It's just that you are using decimals instead of using. I didn't know that could. I didn't know you could just translate it over to that side and it will maintain all the same properties. Oh, it's still the same thing. Huh? Yeah, it's still the same. Right, XOR is like. XOR is give me something. If you do the XOR, you get something else, right? Then if you bring the results and you do XOR again, you get back the original thing. So it's literally the same thing. It's just that it's a different, like A will always be 101 will always have a unique rep. I think I get it. It's still the same thing. So the two of them have exactly the same method. They just like implemented it differently. Who else? Huh? What's even what? Your own? You just solve it. You have not solved it now. You don't even know how you do the swapping. So there's another idea, right? That he came up with partially. No, you have to use bitwise at some point. So explain it. Explain it.
So one thing I noticed was that it works for like the last index. Like there's a function called even odd, even odd, even odd, even odd. So at the last index, it will always work. So 0, 0, 0, 1. So if you want to evaluate at, for instance, let's say C. So if you want to evaluate, so let's position it. Can get a position it
Anyway.
like odd, like just odd, order it with their indexes.
Okay.
Yeah.
Right?
Yes. So one thing I noticed was that if you want to evaluate for C, right, it's going to be 0, it's going to be just 0, 1, 2 to 3, 4 to 5, then 6 to 7. So if it's, let's say two variables A and B, so it will also, if you do for B, it will just be 0, 1, 1, 0, still the same thing. So now,
So let me show that. Right?
yeah.
So the pairing is also 0, 1, 2, 3. Do you get?
Yes.
So you're saying that the last, if you're always partially evaluating on the last side, it's easy to know what the pairing
It's
is.
easy to know what the pairing
You
is.
just grab them 2, 2, and that's the pairing, right?
Yeah.
Okay.
So now, since that's how the pattern that it follows, if I want to evaluate for B, for instance, now what I'm going to do is that I'm just going to swap C, all the row, like the whole row for C, I'll make it B, then carry B to C, then I'll just do the pairing the same way.
Do you get what it means? Like I think it's easy. So this is what he wants to do. This is what he wants to do, right?
Yes.
So let's say you had two variables 0, 0, 0, 1, 1, 0, 1, 1, right? And you wanted to evaluate at C. We know how to do that already.
Yes.
Now let's at B. Sorry.
At B, yes.
Now let's say you wanted to evaluate at
A.
But let me give value 0, 3, 2, 5, right? Now if you want to evaluate at A, you want to do a swap. So the Boolean hypercube will change. It's not going to be 0, 0, then 1, 0, then 0, 1, then 1, 1. So that will also mean that the array would change, right? So 0 will be here, 2 will be here, 3 will be here, and 5 will be here. Then it will not pair 0 and 2 and pair 3 and 5. Do you get it? Now, you got the idea. Figuring out how to do this swapping is not so easy.
It's
So-
all for three. Yeah.
0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You wanted to evaluate at B, right?
Yeah.
So I don't know which one what one are you going to swap with?
You swap
Okay, you swap
with
C, then C goes there, right?
C will go there.
So what it does now?
It will even and odd.
No. Yes.
Yeah.
So yeah, it depends on how you want to do it. So he wants to always partially evaluate at the end. If you always want to partially evaluate at the beginning, then you can swap to that position. You get? So it's like it's relabeling its polynomial.
So you're swapping the last bit with whatever
You
target
care
you
about,
want.
yes. And then you just use this one algorithm for that target. So now if you wanted to do this, let's say you wanted to swap B with C, it's now be 0, 0, 0, 0, 1, 0, right?
Yes.
0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. I gave him partial because he has not figured out how to do this swapping.
When you also evaluate that,
If you want to evaluate at C,
That's
you don't swap against it. It's already there.
I think you can
where do you
find
get that idea from?
Yeah?
Where do you get that idea from? You've done it for a bad man.
So Aquox, right?
Someone can write it.
This is how Aquox does it. Yes. This is how Aquox does it. So let me show you. I was showing him this morning. So this is their partial eval here. All you need to look at is this B. This is just like the even.
Can you expand it?
Sure. Better. It's not better. Better? No.
No. Yes.
Better?
Yes.
So this is the even. And then it's just the even plus 1. Right? Like if B is what? I think B will be 0 at first. So that will be give you 0. 0 shift 1 is 0, right? Then 0 plus 1 is 1. So this is taking 0 and 1. Right? The next thing will be 1 shift 1, which is basically 2. Then 2 plus 1, which is 3. So it's doing 0, 1, 2, 3, 4, 5. And it's always doing this, regardless of where you want to. So the thing now is that it assumes that you are partially evaluating at the last side. So they have another function called relabel. Yeah. So relabel is the one that's going to do the swapping. Then this is the logic for relabel. If you had come up with this, then I'll say, okay, yes, it's correct. But you didn't come up with this. This is complicated. So try and figure it out. Complicated. So this is what they used to swap. Like to swap. So if you want to partially evaluate at B, you first of all call this to swap B with C. Then you now call their partial eval. You get? So you use one function to your partial eval only works with C, but then you move everything you want partial evaluate to that side. You can now run it there. Yeah. And it's really fast. It's really, really fast. But the new one I'm using now is as fast and sometimes faster than this. So there's another way.
That's why they're doing it.
Does it make sense? Yeah. Oh, you have another way?
Yes.
Mad though. You guys are coming up with different.
Those that have not implemented this. So just write out the
Boolean hypercube,
using
right?
that same boolean of hypercube for it for three values.
Okay.
Three variables.
See how we feel.
So you want 0, 0. You want this?
Yeah. So I noticed something, a pattern, that from the first four,
Yes.
if you are looking for A,
Yeah.
the first 4 is 0.
Yes.
That is the first bit.
Yeah.
Then the second 4
Yeah.
is 1.
Yeah.
So the pairing will be the first. I divided it into 2.
You divided what into 2?
I divided this boolean hypercube into 2.
Okay.
So the first one
Yeah.
and the second one, if
Yeah.
you pair them together,
Yeah.
you'll be looking for A.
Okay, so what you did is that you just broke it.
Yes.
You just broke it here.
Yeah.
So it's now like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right?
Yeah.
Then you also have another one here. Right? Then you
Yeah.
just. Okay.
So if
How
you
you for
evaluate,
B?
huh?
Yeah.
If you evaluate at A,
This how.
yes, that's
Okay.
how you get it. Then
How do you
the
for B?
value you get for A after evaluating at A. After evaluating at A.
Mm-hmm. no, continue.
After evaluating at A,
Yeah.
then the array you get for that one,
Yeah.
you evaluate B at that array.
Like, I didn't evaluate, right?
Hmm?
What do you mean evaluate B at that array?
If you evaluate the partial value,
Okay, partially evaluate B at that array you got. Because now you are partially evaluating A.
Yeah, so when I'm done with this, right, I'm going to get a new
Yes,
array, right?
new array.
That is just 0, 0, 0, 1, 1, 0, 1, 1,
Yes.
right? Uh-huh.
Then you still use that same pattern, divide it into 2. to evaluate from.
So now what you are talking about now is like full evaluation,
Yes.
right?
No, it's partially.
Yeah, it's partially from the front.
Yeah.
But now, what if I wanted to just partially evaluate B straight away from this?
Okay, for me, what I saw is you divide it into two.
Okay,
Then
I,
the first part, you still divide that first part
into two. That would for
second
B.
one.
Yeah, that makes sense. That makes sense if you are going from the. But that's for full evaluation, not for partial evaluation. What you are doing is you are doing full evaluation via partial evaluation, right? But you are only able to partially evaluate at the front, yeah. But then we wanted you to be able to partially evaluate at any, so either from the front, the middle, or the end. Do you get? But that works, and that's sufficient for like some check. It's actually sufficient for some check. Yeah. Another method.
I was able to like evaluate that only B, evaluate that only C, using the same method.
Using this same method.
Yes.
So what's it? You have another method now.
Since you didn't figure out how to do B and C alone.
What if you want to evaluate at just B? You can't just divide it in half, right? Can you?
You can.
Oh, yeah. Tell me. How do you do that?
So you could just divide it at 2 raised to power the index.
Yes.
Sorry.
Okay, wait. This is like how Uche did it. Not this Uche. The other Uche. So let's say B, right? So that would be 2 to 1. So that was
you take
2.
like- yeah, each 2.
Pa.
Yeah.
So how do you pair?
So do I
Recursively.
yes,
Okay.
I do the one.
I get what you mean. So what he's doing now is that wait. So it divides it by the power of. So for A that would be what? 2 to the 2, right? 2 to the.
Sorry. For A,
That's 4. So that's half. Then for B is 2 to the 1, and for C.
For C, 4 to 0.
Okay. So now you're going to get 4 arrays initially. No, for B now. For B, it will be 2 every time.
Yeah, so it's everything.
But you said you divide by 2 to the 1.
I had 2 arrays, then as I divide it, I put first
Wait.
one on one, the second one on one.
Wait. So you're starting with an array of 8 elements.
Yeah, yes.
So I'm evaluating at B. What do I do?
So I was saying you first take the first 2 points. I put 1.
You take the first 2 points.
Yeah, like 2.
That's 0, 0, and 0, 0, 1. Then you put that where?
I didn't.
Don't worry, you can explain it. I believe in you. So you take the first 2.
Yeah, so that first 2
No, just the intuition now. I think it will work. There's a way that this will work. I just need you to articulate it.
So when we take the first 2,
Yeah.
I remove them from the
Yeah.
so then I go to the next 2 again.
Yeah.
Remove them. Just
So you
like
create 4 arrays.
no,
It should be 2
If it's 2 arrays, how is it going to be 2 arrays when you have 4 items? So are you merging some of them?
yes.
So which ones are you merging?
So let's say the first part now is
This.
A.
Let's say this. Let me just name them. So this is A, B, C, D. Halves, right? Or quarters. So what do you do with them?
So it's going to be like the first one from A, with B, C, D, then
How about you take
for
the
the other one.
first
First one from each, yeah.
Yes.
and merge it into one?
So this is 0, 0, 0, which is this.
Yeah,
Then 0, 1, 0.
yeah.
Then 1, 0, 0.
And 1, 1, 0.
1, 1, 0.
So now that way to beat the other ones, the second point. So just get them each.
Okay.
Then for C, there'll be like 1, 1, 1, 1, 1.
We're still evaluating at B. Is this the pairing for B?
You can pair them.
Oh, this is the pairing? No, this is not the pairing for B.
This is like the first.
Yeah, in the first one now.
This
Oh,
for C.
fair from this
This
process.
for C.
Oh.
This for C.
Oh.
That's not recursive.
Yeah.
Is it recursive?
I'm using while loop.
Have you pushed your code?
I just
Okay,
figured
okay,
it
okay.
out right now.
I don't know if this will always work. So if you wanted to do for C, how would that look like?
You saying to what I would like, the first array will just have 1 item, 1 item, 1 item each.
Right? So we divide it into how many? 1, 1.
Yeah.
So there's no need to even visualize that. So how do I now pair them?
You're going to take like I plus 1. It should be like the same method from the other one. No, not really getting out to explain it.
For
But
that,
it works on code sharp. This is like 4 bits and 3 bits.
I don't really get it.
Sorry?
I don't really get it. I don't really get it for like C now. I'm assuming okay, you're going to divide with 2 to the power of 0, right?
Yes.
So that I'm assuming that you have a line here, right?
Yeah.
So how do you now choose what should go in one half and what should go in the other half?
Okay. Let me just maybe like
You
run
still
down
choose the first in zeros member of each box
Yeah.
and zip it together.
No, but see now, they're picking the zeros member of each box and putting it in one array. Then they're picking the first member of each box and putting it in another array. Oh, maybe not.
No, like you need to do this one. So if you collect this two, collect the next two, collect the next two.
Yeah, that's
And you ask for
I see now. I see now.
my code. I'm just taking
I understand it now. 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 Oh, so the way we did this was wrong. Yeah, what he's really doing is you're pairing this with this, like
Yeah.
straight away.
yes.
Yeah, they are pairing this with this.
Yes.
They are pairing this with this and pairing this with this. So this one, so you pair this with this, pair this with this, pair this with this, pair this with this. Yeah, that makes sense. But then does that mean that you're generating like a
So I don't really have like
you don't need to generate anything
one
actually.
array on me. I'm just taking the indexes. Then once I do them, I will reduce the index again. Give
So
them-
for the length of each array, I'm basically just taking the
There's
index
no-
to
there's only one array, just the first one.
Okay.
Then, so I'll take, let's say now for, let's work with Kotlin.
Yes.
I'm just take down the item at 2 is power 2, which is 4.
Okay.
I'll move, so I'll reduce that power, like I separated it.
Yeah.
The 2 is power 4 to come to since I've done some items, then I'll take this one. Like that, same thing for 2, same thing for 1, same thing for 0.
So it's something like, are you mutating anything?
Yeah. I'm getting this particular, this one. This particular array.
I think I get what you're saying.
So how do you now get the
Out.
yes, you say you divide the first array.
If you do 2 raised to power 2, it is dividing them already. Like to start from 4, index 4 is the first 1, 0, 0.
Oh, okay. You're not like creating a different
No, I'm not creating different array.
you're just
Just
getting
the
in
same one. Yeah. Just the same one.
Do I give you two? Yeah, sorry for the line. Don't line is seven. I don't think it's nothing to just.
Just the name.
What's the name of it?
I didn't see your code. I get the idea. No. I get the idea, but I need to see how you actually
Yeah.
implemented the idea.
Small.
All right. Any other?
Yeah.
Wait.
Okay, divide the if you have like 4 or 2 or 3 variables, right?
Mhm.
If you select, okay, let's say 3 for in this example.
3 variables.
Yes, just for the
Okay.
if we want to partially evaluate at let's say B now.
B. Okay.
What I did, I removed all the elements in index 1 because it's 0, 1, 2.
Mhm.
So now when you remove all the elements in index 1 at index 1, rather,
Okay. So you have a vec of
Yeah.
the numbers, right? So the Boolean hypercube is actually like a vec with things like this, right? Okay. I'm listening.
So when you remove at index of B,
At B, yeah, B is equal to 1, yeah.
so you have 0, 0,
So this goes to 0, 0.
0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, and 1, 1.
Yeah.
So you can easily
Identify the pair.
for the hypercube that are equal on like using code, can use the find. Then when you have that, you evaluate
Linear interpolate and evaluate.
what is it?
That linear interpolate and evaluate.
Yes, yes. So you can just use the first one is always 0 to 1 because 0 comes first. Then
Yeah.
the next one will be 1, then it would be
Basically, like this, let's say this one is y1,
yes, 5
and this one is y2. Then you just do like your y1 times l0. Does it make sense? So all she's doing is that she's just removing the target. So she has a vec of all the balls. So she just removes the target and then takes the ones that are equal at the end of the day. Then you just pair it like that. Does that make sense? She has a vec.
Okay.
It's not like bits. It's just a vec. So she just removes it. But there will be a way to remove it with bit manipulation. Yeah. Because what you are doing is similar to what I'm doing, but the opposite. No, the opposite of what you are doing, but also in bits.
So that means you are taking instead of removing.
I'm adding instead of removing. So this is what I'm doing. Is there any other? You had one?
Yeah, like
Yeah.
mine, the way I did mine was relatively same, almost same way, except for the bitwise operation in that
The same way we would.
with the first pattern.
Oh, of course.
Yes.
Yeah.
So the only thing that I changed was the bitwise
The or?
operation. In that I just used the power.
Okay.
The power calculation for two things.
Okay.
To get the B value and to get the next Y value and stuff like that. So
To get the B value. What
like
is,
to get the Y2 value and to get
how do you get the y2? Is it by ORing or just by summing?
by okay so what I did was I took it's literally an array.
Yeah.
So the integer itself. So what I say the first value is 0. So give me this value at 0 in that array.
Mm-hmm.
And then the next value will be plus that power.
Plus.
Which is, yes.
Okay, then you get the
So that
y2.
one which will give me the Y2.
Yeah. So it's using plus as or in the first one. Does that make sense? So it's just the first one, but it's using plus instead of or, which still works. But and you're skipping, right? Are you skipping
Yes, I'm skipping. Once I get that the value is divisible.
by the power
By the
plus?
power.
Okay.
Then
So that makes sense. So this is how I'm doing it. What I'm doing is this. So you know, the idea is coming from this, right? Let's say I had a straight line. Okay? It's going to be 0, 1. If I wanted to get the next Boolean hypercube, I'm just going to duplicate this line, right? 0, 1 also. But then the top one, I'm going to add zeros. And in this one, I'm going to add ones. So this means that from a lower dimension, you can get the values in a higher dimension. Okay? So what I'm doing is, if I'm supposed to generate the pairing for B in 3 variables, I know that B is going to be in the middle, right?
Yes.
So what I do is that I iterate over 2 variables. So I'm supposed to get something in 3 variables. So I'm just going to iterate over 0, 0, 0, 1, 1, 0, 1, 1. But then I'm going to generate 2 things for each of these things here. So 0, 0, I'm going to now add a 0, and I'm going to add a 1 in the correct position.
Okay.
Do you get? So this 0, 0, I'm going to add 0 in the B position,
Yeah.
and then I'm going to add 1
0, 1, 0.
in the B position also. Does that make sense? So this one is going to be 0. It's going to be 0, 0, 1, and it's going to be 0, 1, 1. Then this one is 1 0 0 1 1 0, and this one is 1 0 1 1 1 1. So now it's just like n over 2, and then I just like do the bit insertion. Does it make sense? The idea should make sense. How to insert it might not necessarily make sense, but the idea itself, does that okay?
Are you recording this?
Yeah, I am. So I'm basically using dimension less. That's like if I'm supposed to generate something pairings in 3 variables, I will iterate over 2 variables, and then just insert 0 and 1 in the correct section. Like if you look at the pairing that we have here, like this for A, right? Right? So that means the only thing that's changing is just this 2, right? But if you look at what is remaining, it's still 0 0. Does that make sense? If you look at this other one, this one is changing with this, but what we have left is what? 0 1. And likewise this, what we have is, and this we have, so I'm just doing the reverse. So I start with this, and then I just place the bit where I need it to be. So if I'm supposed to generate the pairing for C, I'll do 0 0 0 1 1 0 1 1, but I'm going to add a 0 to the back. I'm going to add a 1 to the back. 0 1 0 1 1 0 1 0 1 1 1 1. So just add 0 here, add 1 here. For A, you add to the front here. So when I do for A, you do you just rewrite it, to be honest. Same thing. You'll be using dimension 3 as your base. Yeah. So you don't the distance is just numbers, really. I'm working with the bits directly. So I'll figure out the length of the lower dimension. So 3, you know, it has 8 elements. So, but I'm going to work in dimension 2. So I'm just iterating from 0 to 4. Then I'm doing the bit manipulation on the decimal directly. Yeah. So this one is just going to be like 0 1 0 1 0 1 0 1. Does it make sense? So you just n over 2, and then it's always like.
So it was C.
Yeah, you add it to the back. You add the bit to the back. If it's B, add it to the middle, and if it's A, add it to the front. How do you do the bit insertion, right? So I'm using the bit manipulation techniques, right? I think it's pairing in there. So if you look here, can you see it? Can you see it? Are you sure? Okay. So this is the method that can insert a bit into. I don't even know how this works anymore. But what I do is that I move. So let's say I wanted to insert in the middle. I will delete the last thing. I'm deleting it with the shift. So I shift to the right. Every time you shift to the right, it removes something.
Sure.
So I shift until I'm at the point where I need to just insert at the back.
Yes.
Then yes. So I know exactly what I'm doing now.
Okay.
So let me now show you in the notes. So what Max does is that it creates a number of a certain length. But I'll show you in the. Let me first show you the idea, then we'll now see how. So let's say I had 0 0 1 0 1, right? And I wanted to insert a 1 here, so that I'll get 0 0 1 1 0 1, right? That's the goal. So what I'll do is I will try to forget the low and the high. So what I'm trying to do is I'm trying to break it into two parts. I want 001 and I want 01, right? So I break it at that point. Then when I break it at the point, I now want to add whatever the bit is here. So let's say I wanted to add 0 to be this. Then I'll put the other one back in there. That's like the idea. Does it make sense? So I split it, then I combine everything. Yes. Yes. Yeah. And then you combine the other one. Yeah. So now let me now show you how it's actually done. So I think I'm calculating it based on the position. So let's say I want to insert that position. I don't know when I'm going back or front, so I can't remember. But let's just say I want to insert that. Let's just assume. Right? So I want it to now be at position 2 from the back. I think that's too confusing. Let me just say, you know where I want to insert it, right? So what I'm going to do to get the thing at the top, that's like the 0, 0, 1, is I'm just going to shift. I'm going to do a right shift to delete the last 2, right? So I just do a right shift 2 times, right? So that would delete the last 2. So I'll just be left with, yes. Then to get the last 2, I'll use a mask. So a mask is just like a certain number of 1s. So now I only need the last 2, right? So I'm going to AND with just 2 1s. So that's like 0, 0, 1, 0, 1 and 1, 1. Why the rest of it is 0? Do you get? I know AND, both of them have to be a 1. Is it AND I'm using? I'm coming. Yeah, it's hand. It's hand. So that means this will be 1, 1, right? That will be 1. And this will be 0, 1. That will be 0. But the rest of them is going to be 0. So this basically is like the low bits. Yes. So now I have the low bits. Now I want to reconstruct. Okay? So I'm going to shift this. So this one now is like 0, 0, 1. So I'm going to shift it and create enough space for the low bits, but also create enough space for the extra bits that I'm adding. So before I had to shift right by 2. But now I'm going to shift left by 3. Because I'm adding 1 extra bit there. Yeah. So I'm going to do 0, 0, 1, shift by 3. So it has like 0, 0, 0. So this is where the low bit was originally, but I've created space for the new bit. Then my new bit, I'm going to shift it 2 so that I keep space for the low bit. So that's going to be, let's say I want to put 1. So 1 is supposed to be here, but I'll shift it twice. So it's not going to be, do you get? And then I just put the low bit there. Then all I need to do is just like add or. And this is going to be 0, 0, 1, 1, 0, 1. Right, which is what? Does it make sense? The cool thing about this is that it's just bit operations. Bit operations are really fast, like just 1 clock cycle for each of them. So that's why it is really, really fast.
So that means you're always going through 4 times to get the possible parents of 1.
Yes. So if I'm trying to get parents in 8, I only need to look 4.
4 times.
Yes. But I'm only inserting 1. What you could do is that you could call this insert bit function for inserting 0 and inserting 1. But you don't need to. You can get 1 from 0, maybe using like your techniques where you can get the opposite pair. Right? So that you don't have to like do multiple bit operations. I just do 1
I just flip that bit.
Yeah,
when
exactly. Does it make sense? But now we have a lot of pairing.
Sorry, but it's not always do everything in one line.
Oh.
Since right shift is multiplication.
What do you mean?
No, sorry, right shift now. You did right shift.
Yeah.
So it's division.
By 2, yes.
Yeah.
2 to something.
Yeah, so like, okay. So what I'm saying basically is, like, to get high now, value shift to the right.
To delete the low, right?
So
Yeah.
that's still division.
Yeah.
So what if you now say value
Yeah, right?
Yeah, so you put it there.
Uh-huh.
Then that's height.
Uh-huh.
Then I don't know what you did now that line.
That one is and.
So that's then
With
the mask.
max
Then you
is
said you got the mask with the initial value and
the max is the length of the low, right?
yes.
So you just create ones that length. So if you have like 3 bits in the low side, you create 1 1 1.
For that.
Yes.
Right. So that one and the initial value and that mask.
Yes, that will give you
right?
the low.
That'll give
Yeah.
you the low. So it will be like value divided by 2 is the power index, then plus which is all the all,
Yeah.
then value again and mask index.
You're saying that just rather than writing in 3 lines, writing in 1
No,
line.
actually I didn't know you wrote it like this. I was thinking the way you explained it.
Oh, okay.
Yeah.
Yeah. This one is just for readability because technically I could have replaced this high with like val
Yeah.
shift this. Then I could have replaced low with that also. So technically 1 line, but it's just not. Rust compiler will compile it down to something succinct for me. But division is slower than yes. Like multiple cycles.
Okay.
Yes, even if you are maybe the compiler might see that you are dividing by a power of 2, and it might convert it for you to bitwise. But if it gets down to like the processor directly, division is going to be slower than bitwise because we have to think about remainders and all those things, and that's like more machinery, which will make it slower.
For the pairing, right?
Yeah.
You can also use like listed loops, but that would not be much.
So you loop and loop, right? Then you compare something. How will you compare?
First we go from like 0 to the number of the next.
Okay.
Second loop starts from the second two.
Okay, yeah. So that you don't check it back.
Exactly.
Yeah, you could do that. It's just not efficient, but you could do that.
That was like
So we're good, right? We have like a couple pairing functions. So just pick the one that feels most intuitive for you, and then use that. Then benchmark, and just know that okay, if you didn't use the different methods have different efficiencies. So when we get in front, like when we're doing like GKR, and then you try and prove something, and realize that this thing that you're proving is taking 1 hour, while another person's one is taking 5 minutes, then you know that okay, you now need to go back and start like tweaking some things to make it more optimal. Huh? Yeah. when we finished our first implementation, because we don't even know about evaluation form multilinear. When we started with coefficient form multilinear. So we're literally doing coefficient form. I did dense, then you did like the monomial one, and then we now use that to try and do GKR. We tried to prove GKR with that. It was really slow, like really slow. So now I have to go and figure out like what can we do, and that's when we now like discover like evaluation. Cool.
For this thing we did now, if you want to like pass some values, like for example, 3 degree.
What do you mean by 3 degree?
Like 0 1 to 3. That is evaluation point, something like that.
0 1.
That one that has like
Okay, 3 variables.
yes, 3 variables.
Okay.
So I just like get like final result. So you do the first partial evaluation.
Yes.
Get another 4.
Yes.
Then you do it again, get another 2.
Yeah.
You do it to get the final point.
Yes, that's one way to do it.
Yeah. Do you just do it one by one, get the result into it, or do you just get a function that does everything at once? So once you have
Yes.
like 3,
It's to do the 3 at
times.
once.
So
Yes.
you have like 2 times.
I think that's what I did. I did the one that you can call partial evaluate on more than one variable, rather than calling it on multiple variables. So yeah, so you see my partial evaluation is taking assignments, not just one assignment, one variable. So the way I do that, let's say I have A, B, C, D, E, F. You can say that I want to start at C, and I want to evaluate the next 3, right? So you are evaluating C, D, E, F. So that's how I did it. I think Francis you can specify randomly the different points that you need. So you can say I want to evaluate at A, I want to evaluate at D, I want to evaluate at E. But my one, I said that it must be continuous. Like If I variables are multiple, they must follow each other. So C, D, E, for example. Both of them work. It's just that some check only needs. Some check does some check even need multiple? Yes. When you are doing GKR. Because the variables might use more than one bit. Yes.
Follow for the full evaluation now.
Yeah, full evaluation also work for it. So if you look at my evaluate now, my evaluate is just calling partial evaluate 0 with all the assignments. There's no for loop, no nothing. Partial evaluate will just handle everything at once. Then there's an optimization actually. If you try to partially evaluate a variable at 0 or 1, you already have the answer to that. You don't need to actually do that linear interpolate and evaluate thing. You could just return. Yeah. Alright, sounds good.
So moving forward, what we need is to be able to evaluate, partial evaluate points that you pass at points here that you pass in. Not like you can evaluate one, sorry, A, then B, then C, like I don't know yourself. You cannot if you want partial evaluate, you pass in all the values together, not that you pass in one value, then evaluate remember that
The results
yes.
in a partial evaluate. You can do that now, right?
Okay, so
Yeah, you can do that, but
then you can talk about GKR.
yeah, so in GKR, there are variables like on the protocol, like when you're looking at the protocol itself, you're saying that oh, this function is f of b c, b comma c, right? But that b is actually like 5 other variables in your actual polynomial. So there's a difference between how it's written in the protocol and how it actually looks like in your implementation. So in that case, you'll want to be able to evaluate multiple. So you could still use yours. Like, let's say like in GKR, I will tell you that okay, partially evaluate this function at these 5 values, but the 5 values are always going to follow each other. So you could do it so that you change your implementation to be able to take 5 things and partially evaluate, or when GKR gives you those 5 things, you can loop over and then just evaluate each one. So you can still use the current one to implement that, but you can also modify it to make it faster. So it depends on you. Okay. So for those that have not figured out pairing index, you have a lot to choose from now. So just choose the one that works for you, then try and implement your multilinear polynomial before Monday, please. Because by Monday, Francis is going to take you guys on some check. And some check uses multilinear polynomials. And the implementation is supposed to happen like that day / the next day. Some check will need to take like 2 days, potentially. Then after that, we're moving to GKR. We're moving to GKR.
As you are progressing, this thing is getting better.
No,
The thing is that, you know, all these things are, this multilinear now,
It's giving me a headache.
Don't worry, that will be easy.
Sorry, which one is harder than this one?
Everything coming now is harder than this.
But it won't be hard for you because, I mean, what you have done now has made it out.
So we should just select one.
Exactly, that's how it happens actually. Like at the beginning, there's this like, you're not confident, right? The more of these things you check out, your confidence increases. By the time you are done, you'll feel like you can do anything. You get like, you'll be like, I can implement anything. And that's actually the most important, like, if you guys even forget everything you have learned so far, but you come out of this with just knowing that, okay, any technically hard stuff, if I put my mind to it and I put in time, I'll be able to implement it. You're fine. Because we just go back and redo everything. So that's the most important skill. Because if you're just like memorizing or you're just like doing this and you're not actually like growing, then once we're done, you're done.
Yeah.
and that's no way, because the field is so, there's no way we can teach you all of ZK. See the pace that we're moving at. We have done a lot in such a short period of time. Like months of trial and error between me and Francis. You guys have gotten it in like a couple weeks. And then it's not like it's still not enough. Like the space is still so big that if we continue at this pace, we cannot still cover the entire ZK space. So when we're done, you will now have to work hard again, continuously. And the hope is that we'll get you guys to our level. Then people that want to continue learning can now like join us and be learning with us, right? So that like more heads are now like learning together. So when we're watching one video for 2 hours and we only watch 4 minutes, it's all of us that are going to do that. So there's still a lot. There's still a lot. Even me, there's still a lot. Like it's still so much. Still so much. Huh? It's still young. It's still young. There's still so much. It's crazy. It's crazy. Yes.
Are you working already with ZK?
Huh?
Are you working with ZK?
I was working at school, yeah, with ZK.
ZK?
Yeah.
Well, your energy is okay. If you can work.
The goal is to build a research lab
Let's go.
that can compete against like all these global research labs and build it with like homegrown talent, not just like, oh, you now like raise money and then you hire people. Like we're not dumb now. Are we dumb? We're not dumb now. We're not dumb.
Just getting started.
We can do this thing. Eh?
We just getting
Exactly.
started.
They don't have 2 heads. It's just that we usually don't have the would I say the opportunity to try these things. Like we're focusing on other kind of problems that we never get to the point where we actually apply ourselves to like complex stuff like this. So it's not like, I feel like if we apply ourselves to those, there's no reason why we cannot achieve like the same level of results or even better. Like there's no reason. It's just that like now ZK, how many people know ZK in Nigeria? So how do you even want to start? Like how do you want to start? The goal was to just go straight, like I wanted to just like research. Then I realized that 2 of us is not enough. There's just no way that both of us will be able to like cover the entire space in any reasonable amount of time. Like it's just not going to work. So we now say, okay, the first thing we need to do is just like try and like get more people to know this stuff. A lot of people. Not a lot of people are going to follow you on the journey, but you will find like 1 or 2 couple people that you can now like, you know, brainstorm with. Like that's what I really want. Like being a room of like 5, 6, 7 really smart people and just like try and understand this stuff. Because once you understand it, you can now like make use of it to like do whatever it is that you want. So or just give up and just go to the US. I'm serious. I've been weighing it, especially with this Trump thing. Like the US is going to be like such a like the land of opportunities there is going to be crazy. It's not like. Well, we'll see. We'll see. It's still like question mark. It's still like question mark. Oh man. Alright, let's look at bit ups. So anyone you don't understand, you can just let me know. So I'll first teach you guys how to represent stuff in binary. That's what I've been doing. So like every number, at the end of the day, at the bare metal, everything is binary. Like all your structs, bools, every single thing at the end of the day is just binary, right? That's how the computer works. So let's say I create a variable called a, and I make it a U8. So U8 just means binary of length 8, right? So it has 8 bits in it. So let's say I put 0. I don't know, is there a way to print it out like to show the... I wanted to show all of them. Doesn't show it. Francis, is there a way to make this show like 0 is in the U8. I wanted to show all the all the 8 zeros. I think there's a way now.
Yeah, 8 zeros.
Yeah, I think you put something in front.
Yeah, you put number. Yeah, like that.
No, but you're close. I know I've seen it. I know I've seen it before. I know I've seen it before. This cannot work. No, this cannot be it. Yeah, that one I'm trying to. What? How would I specify that? It's a job for ChatGPT actually.
First time.
That feels off. I don't want to write. How do I even ask this question?
So if it is 800, so
Yeah.
it's 08.
Okay. That looks fine. That feels familiar. So this is 0, U8, right? So these are 8 bits, right? 1, 2, 3, 4, yeah, 8 bits for 0. Now let's use 1, right? So if we use 1, it's always at the end, right? If there are zeros in front, it doesn't really matter. It's still 1. Now I want to show you guys left shift. So left shift would push the 1 to the left. It's literally just shifting it. So I can do 1, left shift 1, right? Which will shift 1 times. Can you see it?
So you have a value, then the direction you want to shift,
Yes.
the position where you want to put
Or
it.
the number of
No, number of shifts. Yes. So it will just push it down to add a 0 at the back. Do you get?
Then I mean, that will be 9 instead of 9.
So you mean the decimal? The decimal
The bit now.
will it be what? Okay, will it be 9? No, it's still 8. It's still 8 because it's a U8. A U8 is always 8 bits, regardless. So like if you try, I think if you push, and you have an overflow. You get? When the 1 is supposed to like, there's no more space for the 1 to stay. So I think let's say like we push, let me show you pushing 3 times now. That means that there will be 3, what's this? Okay, let me create another terminal so that I don't have to. Okay, there's no. Okay. So now we did shift 3, right? So that's why you can see 3 zeros behind that 1. Does that make sense? Okay. Now let me do shift. Okay, 5. 5 zeros behind, right?
So shift is just shifting it
Shifting.
full
Yeah.
byte.
Yeah.
Just shifting the bit in full byte.
What do you mean full byte?
Like in one full byte, in one whole byte, is shifting that one bit.
Yeah. So you have like, like I could have used U32, I could have used U64, right? I don't know if you get what I mean. So I'm using a U8, but I could have used like a U32. So what would I do here? Is it this? You see? It's like if I didn't do a shift, it would have just been at the end, right?
Yeah, like even in 32, like in 8 bits makes 1 byte and stuff like that. But 32, I think. So like I was just trying to understand that shifts, like an easy way to just memorize it is that for 1 full byte, it kind of like moves it through the byte.
No.
1 true byte moves it bit by bit.
Yes, it moves every bit 1 step to the left, or depending on the amount you put. So if you left shift by 1, it's going to move every single one of them 1. So now if there was something here, that thing would disappear. So let me now use. So I'm going back to U8 just because it's smaller and we can visualize this more. It's already bigger. Yeah. So now let's say I assigned it U8.max. So this is the biggest U8 value that you can get, which is basically all 1s. Okay. Now let me do a left shift of this by 1.
Is this still 8 ones?
It's still eight elements, but we have lost one value. You get?
It's not like
It shifts it, and then that one just shows it away. Yeah, just shows it away. If I was using a U32, it would have shifted it somewhere else, but it just shows it away.
If replacement is possible, like you just want to remove the function.
Yeah, you can do that with. So there's a book, right? There's this book. It's called Hacker's Delight, right? And in this book is all about bit manipulation. That's literally all that is in the book. So it's just showing you different ways that you can do different things with just bit manipulation. So most people that are doing like compiler engineering stuff, they make use of this because bit manipulation is just way faster than regular arithmetic. So if you can do something with bit manipulation, then it's going to be faster. Hacker's Delight. I'll send it on Telegram. I'll send it to Telegram.
What if you read 9 or 10 here?
Where?
Like 0, 8.
Oh, I don't know actually. I don't know actually. Let me try 2. Let me just see. Huh? And I want to check. Okay. What does that mean?
If you have more than one, it's like
No, it's just the 0 is just a representation. It's still the U8 is still 1.
Yeah, you get still 1.
So the 2
So the 2 is just like.
is just the width. So it's just representing 2.
Okay. So it's saying that print it with a minimum length of 2.
Yes.
Minimum length of 2. But if it has more than 2 bits, then print the rest. Right? That's what I'm thinking, but we have to verify that. So something that uses 3 bits is like 5, right? 5 is 110 or 4. But let's use 5. So now this should print 1 1. No, 101.
That is 1
It should print 101, even though I'm using
Yeah.
2, right? Okay. So that's what happens.
So in this case, you move 1.
If I move 1,
0.
it will be, this is just the printout. It's still U8, right? So it's not going to delete it. You get? It will shift it to the next, yeah, let me do like, shift 1, right?
Can you left
Okay, let's use 255. 255.
The max? Oh, not the max.
Can you left shift it up there? Yes. Like, can you left shift it up there at once? Like 5.
Yeah.
shift up.
It's the same thing.
Can you do it at once? Then?
Yeah. That's what I've been doing since. I just changed it. Good? Should I change it back to 8 or you want to see it as 2? No. I mean like the representation. Should I change it back to 8?
Okay. Now if you move
255 is the max, right? So you removed 1. Yeah.
Now if you move 0.
If you left shift
Yeah, let's
by 1, you will now have everything. So basically everything here would move this way. So this other one now is gone. Then this one will take the place of this. And then they will move, so there will be 2 zeros at the back. You get? So this means that you can make any U8 number 0 by just shifting, I think, 8. I think.
I thought it was just like replacing.
It's in an overflow. No, it's pushing it. Is it 7? How's it 7?
We had 0 at the back before.
So it doesn't allow me to push by 8. It only allows me to push by 7. If you push by 8, then there's like overflow.
So that means if you write like 9 here, it's
Mhm.
going to print the one that you've shifted.
You write 9 where?
You use 0, 8. That means if you write 9, there's going to be 1 and you shift.
I doubt.
Because now
Because
it's
it's-
saying overflow. Does not
I
say overflow.
doubt. It doesn't work.
Still overflow.
Because it's
Like,
still a
you
U8.
use 8, you use 8. You shifted by 8.
Oh, yeah, if I put it. Okay, I get what you mean. I still doubt. Okay, no, it's add a 0. Oh, wait. I should shift what? By how many times? 7?
9.
9.
I should shift by 9.
No, just shift by 1. Basic 1.
Okay, trying to see if
So by 9.
No, by 1.
By 1.
That's because of the representation.
but you still lost the
So this is like a print. It's a print modifier, right?
It was way more than
So 9 is more than 8. You know, U8 is always 8. And then you're saying that, okay, I want a string that has 9 elements. So pad it with 0. Wait, is that in the padding? Might
Put 1.
be.
No, put 1. 1 9.
No, that seems weird. I only know why it's 1 9.
Yeah,
And,
put 1 9. Put it with 1 now.
It's 19 as well.
Yes, you put it with 1.
no, you part of what? You part of emptiness.
So that would be 0, 1, 9 or
Not
what?
0 is
But what of 1? How do you part it with 1? There's no way to part it with 1.
Why is it funny?
It doesn't make sense to part it with
Exactly,
1.
why is it funny with
Yeah, why would you part it with 1? That's
That
true.
was 0.
So I can do like this, right? Wow.
Padding 1 is almost like
You're changing the number.
No, it's almost like when you're doing this 1's complement.
Yeah, two compliments.
So that's to make sense.
Okay, so we understand left shift now, right? So let's now do right shift. So now we have the number, which is 1 1 1 1 1 1 1. Then we do a right shift. If we're doing a right shift, they all move like this. So this one now is getting deleted. Yeah, this last one here, getting deleted. And then there will be 0 that will come from the other side. Yes. So that's the right shift with 1. You see that? Then the right shift with 2. Does that make sense? So this is right shift. What else?
So right shift is like removing the MSB, right? And then moving the LSB.
What does B mean there?
The MSB is like the ones the
Most significant what?
significant one.
Bit or byte?
Bit.
Bit.
Yeah.
Now my MSB I think is used with bytes. MSB. So LSB. It's bits, right? Huh?
Yeah, it was in the Gemini.
Most significant bytes.
Where do you see that?
Is it-
So you can see here now, there's least significant byte and there's most significant byte. So when they're using it in context of this, that B now means the byte. But then,
But the one I was
I guess it's just based on your context.
the one I was talking about.
Yeah, I thought it was just always bytes because I've been using this little Indian, big Indian thing. Okay, so yes.
So I think how
So-
to do the right.
The right shift. I'm coming. So the marks, right? That's just one. Then if I do a right shift, what happens is that this guy gets deleted, then 0 now added to the front.
What if the number was like 1, then 1 to like
You said?
what if the number was 1
Mm-hmm.
and 1 to like shift right?
Okay. So what she said now is that what if this was 1, which would have been zeros with all ones, right? I'm going to move. Right? Now if we do a right shift, we're going to get 0.
All 0.
Yes.
So wisdom, back to what I was saying that so the MSB is right, the left move.
The MSB, depending on your. Yes. There's something. Oh, yeah, continue. I understand what you're saying.
Yeah, so is it because I'm trying to use because I already know MSB and LSB before now.
Yeah.
So I'm trying to connect the right shift and left shift to MSB and LSB.
So now MSB, where B means bit, right?
Yes, bit.
So if you are doing a right shift, what's happening is that the LSB, the least significant bit, that thing is even wrong. It's just but I don't want to hear me say this thing now. And then I was like, I said this. So the LSB, in quotes, will be deleted, right?
For right shift.
For right shift,
Yes.
yes. The LSB will be deleted. And then 0 will be added as the new
MSB.
MSB. Then for left shift, the MSB will be deleted. And then 0 will be added as the new LSB.
Sorry, I thought MSD was the one like leftmost part.
Yes.
LSD was the rightmost part.
For like 5 minutes.
You said MSB is the leftmost, right?
Yes.
Yeah.
So when you did, which one did you do?
So I did right shift now.
Right.
So the LSB was destroyed. And then a 0 was added as the MSB. Why are you confusing yourself though? Just use it directly. And then there's a 0 here.
So let's, I think it's just confusing. From the start, right? We started with all ones.
Let me now. I want to do all ones now for you. So this was all ones right shifted by 1.
So one was the MSD before, right?
Yes.
So when you did right shift, you deleted that.
I deleted the LSB.
The one at the end goes off and 0 is added as the MSB.
You're confusing yourself.
Just like shifting.
Yeah, that's shifting. Exactly. You know someone that's doing MSB?
Okay, so
Come on,
I'm
come
seeing.
on, tell her that her name has a different meaning.
So MSB order is like from here to here.
Sometimes, yes. It depends on the kind of system that you're working with. But yes, it is. For 8 bits. I think for a byte it's always like, but when you're not dealing with more than 1 byte, let's say 32 bytes, the way the computer stores that depends on the endianness. So if it's little endian, then the most significant bytes will be stored first. The least significant bytes will be stored first. Then if it's big endian, byte will not bits. That's why it's so confusing. If we have time, I don't think we'll have time. But what we wanted, I don't know if we'll be able to do this now, but for people that are interested, you guys might be able to implement like a VM, that's like an actual virtual machine, yeah. So like RISC-V, like me and friends have implemented RISC-V, which is like all the ZK companies right now, they are creating ZK provers for RISC-V virtual machines. So you can implement like your own VM, and then you now like Zkify it kind of with like different ZK techniques. But I don't think we will have the time for
Let's say like implement it in Rust.
implementing VM in Rust. So you can use your VM to run Rust code, for example. Huh? Oh, I'm not using Cargo, right? So I'm just using the Rust. The Rust has a Rust compiler called Rust C. Cargo is just to help you make things easier, and so because Playground was not working for us, so I needed like just one file. I didn't need a Cargo Tomo and all those things, so that's why I can't use Cargo for this. So I'm using Rust C to run it. So to run it, you compile with Rust C, then you use your file. So what this will do is that to compile this code and to generate a binary. And to name that binary, just test without the .rs. So if you want to run the code, you now do like dot stroke test. So I'm writing in Vim. Yeah, so just forget this. This is just for me to run commands inside Vim. But this is all you care about. This is what will work on your terminal. And then that should work. So I'm just doing both of them at the same time. So compile, then run. So I don't have to always be doing it at once. So we know left shift, right shift.
Yeah.
What else? Do you want to know and or? Are you interested in that? Okay.
Yeah.
So How do we do this? I'll print out A and then I'll print out B.
Hold on, please.
So let's do and in Rust is this. You do A and B. So just one ampersand. That's and in Rust.
B, you're not printing B.
I was printing A, right?
Yeah, right.
Thanks. And also you can write directly in binary in Rust. So you could literally just write like 0B. So if you write 0B, then you can just write your binary and to be able to store it in a U8. So I can do like 0, 0, 1, 0, 0. I have to do 8. 1, 2, 3, 4, 5.
Zero behind this.
No, the 0 behind is not counted. I don't think. I don't know if I did this correctly though. But yeah. So this is B. And this is A. And I'm doing AND. So this is serving as the max in my previous system, but forget about that one for now. So 1 and 1 is 1. 1 and 1 is 1. 1 and 1 is 1. 1 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. 1 and 0 is 0. 1 and... Does that make sense?
Yeah.
So now OR is going to, as long as there's a 1 somewhere, it will move, right? So if I OR this and this, what will the answer be? No, OR. It will all be 1s, right? Because this one already has 1s everywhere. So to do OR, use this pipe. Huh? 1 pipe. If it's 2 pipes, then you're now doing like logical, yeah. That's like if you know in your if statement you can say A or B. A is true or B is true.
Okay.
Yeah. So we'll do XOR now. So you can see that it's all 1s. But now let's change this a bit so that we're not using the max anymore. 1, 2, 3, 4, 5, 6, 7, 8. But let's now make this 0, make this space 0 also. Right? So what happens when we OR this? To be 1, 1, 1, 1, 0. We'll just do it and then confirm whether the result was correct or not. So there's 1 here, right? So that's why there's 1. There's 1. There's 1. There's 1 here. This one there's no 1 at all. There's 1 here. No 1 at all. And then there's 1 here. So that's OR. Wait, is it making sense?
Yeah.
Okay. So this XOR in Rust. This caret symbol, that's XOR. So XOR is going to, if they are the same, then it will be 0. If they are different, then it will be 1. So they are the same. 0. They are the same. 0. They are the same. 0. They are different. 1. They are the same. 0. They are the same. 0. They are the same. 0. And they are different. 1.
Is there exams? Exams.
I actually don't know. No. We can check though. What's that?
Exams.
Just like that admin negative. No, that's not.
Let me just check like for the list of all the bitwise.
I was just like instead of XOR. There's an exam.
So there's AND, there's OR, there's XOR, there's NOT. So NOT to just flip. Let me show you NOT. What?
Is that what zone?
So this is NOT. It is NOT. So 1 is now 0, 1 is now 0, 1 is now 0, 1 is now 0. 0 is now 1, 1 is now 0.
Why all this many bits?
Many what?
Many bits.
Beats? Oh, many logic gates. Yeah, good though. So then, exactly. So we have left shift, we have right shift. I don't know what this is.
Right shift is 0. Like, what does that do?
What's that? I don't know.
It's like right shift, but something
Oh, the bit shifted to the left.
That's not, there's no O there. Okay.
So I have a question.
Wait, I'm coming.
The bits shifted to the left are always 0.
As opposed to
So please, can you try right shift? I mean,
Let's see it now.
Where's,
Let's try it.
where's the, yeah, we have to try it. Wait.
Have an example.
Okay, no, Jude. Let's try it ourselves. So we have A, right? I'm going to use all ones. Just. So I'm going to do A, right shift, 1, and then shadowing errors.
And then right shift is 0.
Oh, maybe that's it. But let's see. This doesn't work.
No value.
But it doesn't even look like Rust
or
is.
probably they have a way of.
Oh, what is this? I don't think this one will work either because Rust was complaining about the symbol itself, not even the. Is this Rust?
Let's look at it.
Is this Rust? This is Rust. Is this guy whining us?
and it's not in
It's not in his example.
Maybe it's an extended example.
Waiting my car.
So just.
I was there before.
There's in JavaScript. No JavaScript slander. What's the difference? There's no difference now. There's no difference. Okay. Just forget about that. Forget about that. So, what else? What else? What else? What else?
You said we didn't
You didn't write it there. So we're good, right? So then you now use these tools and you combine it in strange ways to achieve
In what?
strange
in
things.
strange ways
strange things.
to achieve strange things.
So how about the
Please, no, I want
Sorry,
to ask a question.
Doing things.
how about the right shift? Like how is it just the same thing as the left shift? Like just
The other
move
way.
the beat forward
Yeah,
right,
instead of
in the right
backwards.
direction
Yeah,
and append 0.
at the front. Yeah. Yeah? Jude,
So if you have 1 0, it's going to become 0 1 0 or
Huh?
0 1.
if you have what? 1 0.
1 0.
And you what?
And you right shift. Is it going to become 0 1?
Yeah. Jude.
So my question was like, when you have so you have like a U, let's say a U8 and a U that's higher than it, maybe a U16,
Yeah.
and then the process of like, my example is I wanted to see the difference between like a signed and unsigned, like what happens, because I remember you talked about two's complements and how like the most significant bit represents sign.
Was it me that talked about that? I'm sure I don't talk about that. But yes.
Well, you talked about
Yeah, it was Francis.
It was Francis.
It was Francis.
they are one. Okay, so I wanted to know
How sign is represented?
not just how sign is, but what happens like when you perform like a shift operation on the sign bit.
Oh, I see.
I feel like it might transform
I see.
from being signed to being unsigned, something like that.
Okay, so let's try it. So let's say A is 5, right? And let's say B is -5, right? So this one is going to be U8. Let's just make it explicitly unsigned. So this is U8, and this one B. And let's print out the representation. right? I'm coming. So this is 5 and this is minus 5. This is how Rust represents minus 5. So they do the 2's complement, I think. So the 2's complement is you do a not. So let's say you wanted to change 5 to minus 5. You not 5 and then you add 1.
To the right or left?
No, you add plus 1. Just like actual plus 1, not shift by. So I think I should be able to replicate minus 5 directly. So let's see U8 now. I want to represent minus 5 inside of a U8. That was going to be like I don't know if this will work. You get?
I think
The plus one is doing what?
So that's how you do 2's complement. When you do the not, that's 1's complement. And to go to 2's complement, you add 1.
To go to what?
2's complement. That's weak. It allows you to do like negative operations easily. So the method of representing signed. So like the hardware doesn't need to know what signed is and what unsigned is. The hardware itself just sees like U8 everywhere. But then it's now like on the assembly layer that they will now have the notion of signed and unsigned. So it's like this standard where if the first bit is a 1, then it means that it's negative. If the first bit is 0, then it means it's positive. So that first bit is now like unused. Like it's not really representing anything anymore other than the sign. Like you have lost 1 unit of data. I don't know if you get what I mean. So normally in a U8 you can represent 2 to the 8, right? Possible values. So like 2 to 8, now it's 2 to the 6 possible values, 0 to 2, 5, 5. But for a signed, that's like an I8, you can use 2 to the 7. So because you have to use that first bit for the sign. It could be like positive or negative. So you can't use it for data anymore. So that means that you can only use the 7 bits for data. So that's why if you check like if I print out the max, right? U8 max, and I print out the I8 max, you'll see that I can represent maximum 255 in a U8, but I can only represent 127 in an I8 because we have lost that bit.
Can you also do U size and U32?
Yes, but it will be bigger. U size and I32. No, U size and I size. Okay. You want to see the max?
I want to see the difference between them, yes.
You want to see the difference between them? Okay. DBG U size. So U size takes the word size of your architecture.
Yeah.
So this is 64, the word size, your laptop or your hardware. So my laptop is 64 bits. Most laptops now use 64 bits. So U size is actually going to be the same thing, should be the same thing as, I've never checked this, but it should be the same thing as U64. Then U32.
But in like solidity, it's not, it's just U32.
I don't know solidity. so wait, sorry. So see U64 and U size, right? It's the same thing. Because that
Almost the same thing.
it's exactly the same
The
thing.
one is longer than.
No, sorry. So see, you know this is U64.
Come back.
Do you understand?
Yes.
Okay. So solidity, the word size is what? 256. So what side is 256? Which means that every operation works with 256 bits. But now here, every operation works with 64 bits. 64 bits. And 64 bits is really large.
So meaning that it's almost not advised. Okay, let me not put it like this. So is it now advisable to work with U-size, knowing that your program might be tested on a system that is actually not the same?
I get what you mean. So when you're working with U-size, you cannot put anything in your code that would force it to be like 64 or 32. Yes, that's right.
And that's what I'm saying.
And it knows
it's
that.
advisable to now do that when, if you code it with your system which is 64, somebody who might be using that program or who might want to run that program might be running on the 32.
It will adjust.
Like, if it now goes beyond like
it will adjust.
bigger than 32 and it's on that person's system, it's going to break at the end of
You are
the
not putting 32 there.
No, I get his question.
No, like you are putting this size, but it's now depending on the system.
And to adjust.
It's not the size that goes all the way.
So
Whatever
whatever
this citizen to take the value of that citizen.
is that value I'm saying now, assuming that that value is
If there's
bigger
a
than
computation that has
U32.
And people with this, so only for the size.
No, my question is that if there's a computation that exceeds that 32 bits which your system has.
And to run differently on both computers.
So
Like imagine like you have a for loop that just adds 1, 1, 1, 1, 1, and stores the result in a mute U size, right? So if we run that on a U32 system, it will run. We run it on a U64, it would be longer, yeah. So you have.
So that means it's not going to be consistent.
It's not going to be consistent, yeah. But do you want to just?
So it's not advisable to use U-size.
I won't say not. Why would you not use it? Unless the only solution to your problem now is to only use U32, right? You should never use U64 basically.
Is your problem that?
But wait, that's what we're using. That's what we're using.
I know, fields.
Field works the same way.
Yeah, field works. This one is more. It's not even a cryptography thing. It's like all over. But fields now. So there are things called big integers. Those ones they use. Like that 256 now runs on your computer, but your computer doesn't actually understand 256. So how does it work? So it's using like, I think 64 4 times. Is this 4 times? Yes. So it's like that. Everything in Solidity is basically like an array of 4 use 64. So whenever you do, that's like an addition or a multiplication, it is doing it with that array of 4. So it gets between like 4 additions or 4 multiplication or more than that actually.
I think you do for mean too.
For mean. What's mean?
Do it
There's always 0 now, right? Oh, but for I8 it won't be 0. But for U8 it will be 0. So for U8 it's 0 because it's unsigned, right? But for I8 it can be negative. So at the end of the day, the I8 is still able to represent 256 values, yeah. But the other half of it is in the negative spectrum, while the other half is in the positive spectrum. But this one, everything is in the positive spectrum. Make sense? Is there any other thing that you guys are curious about? Explain things. I don't know.
So,
that binary operation I would use.
Which one?
That would be the one. Just I just say sorry.
Which one?
Like this 001.
This one?
Yeah, if we like add them those binary.
Yeah.
Give us a result. Can we convert that result to this and see what's the decimal?
Yeah, it's always decimal. I don't know how to put it. So like you could have said let A be equal to 0B0, let's say 101, for example. But if you print this out, you get so there's nothing like decimal. It's all binary, but it's just like it's interpreted. Makes sense. Oh, we're good now. If there's any other question you can just like ask. I think we can stop here. Then you guys can break. Then you come back and continue your implementations. You want to finish up? What do you mean? Like, you don't want to break?